In this section, we're going to talk about inverse transforms and the transforms of derivatives. Suppose the following. Suppose that the Laplace transformation of little f of t is big F of s. So suppose the Laplace transformation of little f of t is big F of s. Well then, what would f of t be? It would be the inverse Laplace transformation of big F of s. Basically, you have functions of t's in here. Oops. So let me write that down. You have functions of t. You have f of t or f1 of t, f2 of t, etc. Now f of t, g of t, h of t, and over here you have another set. It's functions of s. You have big F of s, big G of s, big H of s. So since there's more than the number of letters in the alphabet, we'll call them big F1, big F2, and big F3, etc. So L, the transformation or the mapping L, goes from the left set to the right set. It will take f1 of t and it will map it with some function of s. But what if we want to go the other way? What if we want to go the other way? Well, when we go this way, so let's just put this in blue. When we go from the left to the right, it's out. When we go the other way, we call it the inverse. So in our case, L inverse of f sub 3 of s is f1 of t. f1 of t. Just goes back. So, we know a lot of transformations. For example, we know that L of 1 is 1 over s. And we know that L of t to the n is n factorial over s raised to the n plus 1. But this is just for the counting numbers. We know, for example, that L of e to the at is 1 over s minus a. We know that L of the sine of kt is k over s squared plus k squared. Okay. We know that the Laplace transformation of cosine of kt is s over s squared plus k squared. We even know that L of the sinh, put that h in, the sinh of the angle kt is k over s squared minus k squared. And really want to sneak it in here. We know that L of the cosh of the angle kt is equal to s over s squared minus k squared. So apparently we know 1 and 2 and a third one and a fourth one, 5 and 6, and the one we just did now. So we know 7 Laplace transformations. Well, that means we know 7 inverses. If we know L of 1 gives you 1 over S, then L inverse of 1 over S will give you 1. If we know this one, we know that L inverse of n factorial over S to the n plus 1, that gives you back t to the n. But only when n is a counting number. We have number 3 here. Well, if you interchange these two, the function has to become inverse. It's always been that way. L inverse of 1 over s minus a is e to the at. Number 4. L inverse of this, of k over s squared plus k squared, this will equal to the sine of kt, etc. for the rest. If L of this equals that, then L inverse of that equals this. If L of something is equal to something else, then L inverse of the something else equals, in this case, the triangle. And I couldn't care less what this and that are. I do know that when you go from here to here, the this and the that get switched. And you put a little minus 1 up there. Okay. So, we can now find some Laplace inverse transformation. What is L inverse of 1 over s to the 6? Well, we know that L of t to the n is n factorial over s to the n plus 1. Now, if I'm calling that n plus 1, if n plus 1 is 6, well, 5 plus 1 is 6, then n is 5. If only I had a 5 factorial in the numerator. Well, I can put it. I can put 5 factorial in the numerator. But I better multiply by 1 over 5 factorial. Now, inverse Laplace transformations are also linear. I'm not going to prove that, but they are. We can bring out the 1 over 5 factorial. 1 over 5 factorial times the inverse Laplace transformation of 5 factorial over x to the 6. Well, so if we know this, when I switch these two, the L becomes L inverse of n factorial over s to the n plus 1, that equals 2t to the n. But this here is exactly this, where n is 5, because n plus 1 will be 6. So this here becomes, inside the brackets, 5 factorial over x to the 6. Exactly what we have. So this is 1 over 5 factorial times t to the n. But n is 5. So t to the 5. So the inverse Laplace transformation of 1 over s to the 6 is 1 over factorial t to the 5 times t to the 5. Or you can say 1 times t to the 5 is t to the 5 over 5 factorial. The last acceptable answer would be t to the 5th over 120. 5 factorial is 120. I would like to see an answer like this or that. What is the inverse Laplace transformation of 1 over s squared plus 10? Well, we know that L something gives us 1 over s squared plus k squared. In particular, k over s squared plus k squared. And it is the sine of kt, which means I can interchange those two, and I get L inverse of k over s squared plus k squared is the sine of kt. Now, this bottom, remember, 10 you can think of as square root of 10 squared. So the bottom is s squared plus k squared, s squared plus k squared. But we don't have the k on the top. The k is just a number. I can always put it, even if it was a letter, I can put it. I can put the k on top, the square root of 10. But to justify it, I have to bring out or multiply by a 1 over square root of 10. Now, this 1 over square root of 10, I can bring in front. And it's the same as square root of 10 over 10. And after all, if you have 1 over square root of 10 and you multiply by 1, and I choose that representative of 1, 1 times that number is that number, square root of 10, and square root of 10 times square root of 10 is 10. 1 over square root of 10 is certainly equal to itself times 1. Never be afraid to multiply by 1. Okay, times the inverse transform of this. So that's exactly that, where k is square root of 10. So what's in front, square root of 10 over 10 stays, times this. So that's just the sine of kt. So there's a couple of quick ones. Do some more. Suppose you were asked to find the inverse Laplace transformation of this. Now, when it comes to finding Laplace transformations and textbooks, you're going to see a lot of problems that involve partial fractions. The degree of the bottom is 3, because when you FOIL out, eventually you're going to multiply those 3 s's together and get s cubed. And the top is just x squared. You don't have to do long division, but you want to write this fraction as something over s minus 1 plus something over s minus 2 plus something over s take away 3. Since s minus 1 is linear, which is first degree, I go down 1 degree. First degree, take away 1 is 0 degree, which is a constant. This is first degree, always take away 1, you get 0 degree, so I'll call it b. Same argument for that. Now, I want these 3 fractions to have the same denominator. I want it to have this denominator. So this first fraction in the bottom, so if I want to change the way this fraction looks, And right now, it looks exactly like a over s minus 1. If I want to change the way this fraction looks, I multiply by 1. And if I want the bottom to look like this, well, I already have s minus 1. I need the s minus 2 and the s plus 3. But if what I'm multiplying is going to be 1, well, then I better put the same stuff in the top. If the second fraction is b over s minus 2, b over s minus 2, and I want it to have the same denominator like this one. Well, since it doesn't, I have to multiply by 1. I already have the s minus 2. I need s minus 1 times s minus 3. I need to miss s plus 3. I need the missing factors. If I multiply the bottom by s minus 1, s plus 3, I just have to do the same to the top. I can only multiply by 1. And if the last fraction is c over s plus 3, it's going to have the same denominator as the first fraction over here. Well, I have the s minus 3. I just need the other two factors. S minus 1, S minus 2. And if I'm going to be multiplying by 1, I'm going to be multiplying by 1. Well, whatever I multiply the bottom by, I have to multiply the top by that. So guaranteed this fraction right here, is definitely going to have this on the bottom. And on the top, we'll have a times this times that. This times that is s squared plus s minus 6. Plus, says plus, b times that, which is s squared plus 2s minus 3. Plus c times this, which is s squared minus 3s plus 2. So now, we have at this point that this fraction equals this fraction. And they have the exact same denominators. That means the numerators has to be the same. Can't divide two different quantities by the same value and get the same answer. That is s squared plus 10s plus 25. It must equal to this numerator. Well, this numerator has as squared plus bs squared plus, that should be a c, plus cs squared. So we have a plus b plus c s squared. And then we have some s's, plus we have a s's plus 2bs minus 3c s's. And then we have constants. We have negative 6a minus 3b plus 2c. Well, on the left I have 1s squared, so on the right I better have 1s squared. That is, that should equal 1. Plus 10 s's, plus some number of s's. Well, that number should be 10, plus a constant of 25. That should be 25. Okay, so just to save some space, I'm rewriting what's in here as a over s minus 1 plus b over s minus 2 plus c over s plus 3. And let me erase this. Based on what we have in the bottom, I need to solve for a, b, and c. I know that a plus b plus c should be 1. And I know this equation, a plus 2b minus 3c is 10. The last equation, negative 6a minus 3b plus 2c should be 25. And just so we can talk about these three equations intelligently, let's number them. So the goal is to pick, the first step is to pick two equations and eliminate one variable, and then using the third equation, the one that we haven't used yet. So we're going to pick two equations, say the first two. And we're going to eliminate some variable. And then using the equation that we haven't used yet, namely this one, and one of the two that we have used, namely this one or that one, we're going to eliminate the same variable in those two equations. Well, I'm going to eliminate a from the first two equations. In fact, I'm going to do the bottom minus the top. A minus a is 0 by design. 2b minus b is b. Negative 3c minus the c is minus 4c. And 10 minus 1 is 9. So this gave me one equation without a. Now, using this equation that we haven't used yet, and one other equation, one that we have used, we want to eliminate a. So we definitely have negative 6a minus 3b plus 2c is 25. I'll pick the first equation. I'll multiply it by 6. This way the numbers in front of a are the same. I don't care about pluses and minuses. If this is negative 6a and a positive 6a, I know I'm going to add to kill these off. Negative 3b plus positive 6b is 6b. 2c plus 6c is plus 8c. 25 plus 6 is 31. That gives me a second equation that just has b's and c's. I'm going to make sure I didn't make a silly mistake. Okay. So now, using this equation and this equation, I'm going to solve for b and c. Since this is 1b, I'll try to get rid of the b's. That's 3b's. If I triple this equation, I'll get 3b's minus 12c's is equal to 27. And now I subtract 3b Let me make sure I multiply by 3, 12, 27. Okay. If I subtract, I get 20 C's is equal to 4. So C is 4 over 20, or 1/5. So we now have what C equals. C is equal to 1/5. And I will either use this equation to solve for B or this equation. Now since this one just has B, I'll use that. B take away 4C is 9. So B is 9 plus 4C. Now, if I multiply both sides by 4, I get C is 4/5. Sorry, 4C is 4/5. So I'd love to write a 9 with a 5 in the bottom, just like 4/5 has a 5 in the bottom. Well, 5 times 9 is what goes here. So this is 9, that's 9 plus, and that's 4C, which is 49/5. So let's just write this on top as we get to C is 4/5, and B is 9. Now we just have to find A. Well, I know that when we add them, I get 1. So A plus B, I'll write B as 49/5 only because C has over 5. And it equals to 1, which is 5/5. So we have A plus 53/5 is equal to 5/5. And I hope you realize that A should be negative 48/5. Because if you have 53/5 and you take away 48/5, 53 minus 48 is 5. The A is negative 48/5. Yeah. But of course we do have one typo. That's what happens when you write over things. C is not 4/5. C is 1/5. Actually, let's even change that up here. C is 1/5. So all that happens is that this is 1. Okay, now, so 49 plus 1 is 50. 50 minus 45 will give you 5. So A should be negative 45/5. Or, at this point, A is that A plus this is 50/5, which is 10, and it's supposed to equal to 1. So A is negative 9. And just for the record, that is negative 9. A is negative 9. So we did a lot of work, algebra, and now we have the inverse of a sum a sum of functions of s's. Why do I say functions of s's? To know exactly what that equals, I have to know what s is. Same for those two. Constants can come out in front. So Laplace is the inverse transform of that. And I can bring the 9 in front of the inverse. Plus the inverse of that. So it's the inverse of 9 over s minus 2. But I can bring the 9 in front. Now, of course I don't buy that. B was 49/5. B was 49/5. Plus 1/5 plus the inverse of that. So we can bring the 1/5 out. So it's 1/5 linear transform of 1 over s plus 3. But remember, we know the inverse of 1 over s minus a. It's e to the at. So a is what comes after s minus. That's a. 1 over s minus. That's a. So it's negative 9 e to the 1t, or just t, plus 49 over 5, the inverse Laplace transformation of 1 over s minus that. So it becomes e to the that t, plus 1/5 the inverse transform of 1 over, this is the same as s take away negative 3. So that's my a. It's e to the at. And there is your answer. Try another one. So relearn how to do partial fractions. Suppose you want to do this one. So you want to rewrite s over s squared plus 2s minus 3. Well, the bottom can be factored. Since it's s squared, I'm going to try to think of two numbers and multiply out to negative 3 that add up to 2. And negative 3 and plus 1 do that. So I want to rewrite this fraction as something over s minus 3, that factor, plus something over s plus 1. Since s minus 3 is linear, put a constant on top. Since s plus 1 is linear, I put a constant on the top. And I want to rewrite those two fractions with this denominator. That is, I want to change the way they look. Well, the s minus 3, I need to put an s plus 1. And for the s plus 1, I need to put an s plus 3. Now the denominators look the same. The only problem is that equal sign's not valid. So change the value of the first fraction. You want to change the way something looks, you have to multiply by 1. If I multiply the bottom by s plus 1, I have to do the same to the top. We had on the second fraction was b over s plus 1. I want to change the way it looks. I don't like when it looks like that denominator. I want it to look like that denominator. That is, I multiplied the bottom by s plus 3. I have to do the same to the top. So now we have s over s minus 3 times s plus 1 is equal to, well, when you add those two fractions, since they have the same denominator, we keep them, and we add the numerators. Well, we have as plus bs. We have a plus bs's. Plus, we're adding a, and we're adding 3b's. Now just remember that s on the left is the same as 1s plus 0. That is, the number of s's are 1 and the constant is 0. The number of s should be 1 and the constant should be 0. So a plus b is 1 and a plus 3b is 0. Now when I subtract, the a's are going to cancel. But I hate getting a negative number of b's. Since the bottom has 3 b's and the top has 1 b, I'll do the bottom minus the top. A, take away a by design cancel. 3b, take away 1b is 2b. 0 take away 1 is negative 1. So b is negative a half. B is negative 1/2. Okay. Now, if you take A and you add 3 B's, which will be negative 3/2, you take away 3/2, you get 0. Well, if you subtract two quantities and you get 0, you have to realize actually, the way I factored this was minus 2b. These two numbers, negative 3 and 1, did not add up to 2. Okay, so they added up to negative 2. So let's make believe that was the problem. Sorry. Okay, if you subtract two numbers, this number and that number, and you get 0, you put down the two quantities and you put two horizontal lines in between them because they are equal. So this fraction is equal to this fraction without the ones, that is without multiplying by ones, or even with the ones, but we don't want the ones there. So it's A over, this is A, over S minus 3 plus B, which is minus, so minus a half over S plus 1. Now, the easy part. But it's not going to be easy if you don't remember that the inverse Laplace transformation of 1 over S minus A is e to the at. So it's the inverse Laplace of this minus the inverse Laplace of that. So it's the inverse of 3/2 over S minus 3 minus the Laplace inverse of a half over S plus 1. So you can bring out these constants. Remember, this is 3/2 times 1. This is a half times 1. So I can bring the constant out, but the 1 stays. Oops, there's the constant. And we have the Laplace inverse of that function minus, bring in front the constant, and we have the inverse Laplace of 1 over S plus 1. Just remember, this is the same as S minus negative 1, because we have S plus 1. The 1's understood to be positive 1, not because of that. And if we had S minus 1, that 1 is still positive. We have a rule that says that we can change both of those signs anytime we want. We can change the addition or subtraction symbol as long as we change the sign of the second number. Okay. So now we're ready to answer this. It's 3 over 2 times this. But this is in this form where A is 3. So we get e to the at minus a half times this, the inverse Laplace of this. But that's in this form where a is negative 1. Okay, you get e to the negative 1t, or just e to the negative t. And that's that problem. Let's try another one. Suppose you have the Laplace inverse of 6s plus 3 over s to the 4th plus 5s squared plus 4. Now, what's inside here, it doesn't look like one of the 7 that we know the inverse of. That means we want to rewrite it. S to the 4th plus 5s squared plus 4. This is a quadratic in s squared. Think of s squared as some new letter, but it's being squared. Plus 5 times this new letter, plus 4. I mean, think x squared plus 5x plus 4. Well, that's going to be x plus 2 numbers and multiply out to 4 and add up to 5, or 4 and 1. So instead of s, it's s squared. S squared plus 4, s squared plus 1. So that's the bottom. So now we have that 6s plus 3 is equal to 6s plus 3 all over this. So that's what you got when you factor that bottom. S squared plus 4, s squared plus 1. Now, I want to rewrite that fraction as the sum of two fractions, where one fraction has this on the bottom, another fraction has this on the bottom. But I want these two fractions to have this denominator. Well, they don't. The first one just has s plus 4. So I need s squared plus 1. Oh, you mean I want to change this? Oh, so hold on a moment. Since this is quadratic, second degree, I put linear on top. As plus b. Since this is quadratic on top, I'll put linear on the bottom. S squared is on the bottom. Degree of the bottom is 2. I put degree 1 on top. CS plus D. Now, since this denominator only has s squared plus 1, and I want it to have this, all I need to have s squared plus 4. All I need to do is put s squared plus 1, top and bottom, are multiplied by 1. In the second fraction, if I put in s squared plus 4 in the bottom, now this denominator and this one, they look the same. But I can't just multiply the bottom by s squared plus 4. Unless s squared plus 4 happens to be 1, I can't do that. So I have to multiply the top. So now, this fraction, and this fraction, they both have the same denominator. So 6s, so the numerators must be equal. It must equal as plus b times s squared plus 1 plus cs plus d times s squared plus 4. So here we get as cubed plus as plus bs squared plus b plus cs cubed plus 4cs plus ds squared plus 4d. Combining like terms on the left side. How many s cubes do I have? Well, I have a of them, and I'm adding c. How many s squares do I have? Well, I have b of them, and I'm adding d. how many s's do I have? Well, I have a s's, and I'm adding 4c more s's. And the constant is b plus 4d. 6s plus 3 on the left, well, this is the same as 0s cubed plus 0s squared plus 6s's plus 3. That is, this should be 0, this should be 0, this should be 6, and this should be 3. Now the nice thing here is, although we have 4 unknowns, all equations just have the same 2. That is, this has a's and c's, and this has a's and c's. And there's the only equation that has an a or a c in it. So I can solve for those. Like 2 equations, 2 unknowns. Over here, b and d's, b and d's. Let's solve a and c. We know that a plus 4c is 6. And that a plus c is 0. If I subtract, we get 3 c's or 6, which means c is 2. And we know when we add a to it, we get 0. So a must be negative 2. So I found a and c. Now, we also know that b plus 4d's are 3's. And that b plus d is 0. b plus d is 0. If I subtract, I get 3d's are 3, or d is 1. So I now know what d is. And I know when I add b to it, I'm supposed to get 0. So b is negative 1. So now, instead of in this bracket just writing this, I know that this, which is the same as what's in the brackets above, is equal to this, with 2 changes. We don't need to multiply by 1, and I know the values of a and b, c and d. So it's as plus b on the top, so it's negative 2s plus b is minus 1 over s squared plus 4 plus cs plus d. C is 2, so it's 2s plus d, d is 1, over s squared plus 1. And I can put the closed bracket closer. Okay, so now that I have the a, b, c's, and d's, I could rewrite this nice and cleanly, and things will become nice. I'll take a number of steps. It's the Laplace transform, the inverse Laplace of that. Negative 2s minus 1 over s squared plus 4 plus the inverse Laplace of this fraction. Now you can skip any of these steps that I'm doing. The numerator, we have a subtraction. So it's the same as negative 2s over s squared plus 4 minus 1 over s squared plus 4. Plus, I'm going to do the same thing for the next inverse. The Laplace inverse of 2s over s squared plus 1 plus the Laplace inverse of just 1 over s squared plus 1. Okay. In fact, I can separate it right there. Alright, now, a couple of more minor changes. I can bring out the minus 2. So it's negative 2, so the Laplace inverse of s over s squared plus 4, we should know that one, minus the minus the inverse Laplace of, well, we have s squared plus 4 on top, on the bottom. Now 4 is 2 squared, that is k is 2. If I put a 2 there, that's wonderful. We're going to have to multiply by a half, which I can even bring out in front. Plus, I can bring that 2 in front. Now, let me do so. And we just have s on top. Remember, 1 is the same as 1 squared. Minus the inverse Laplace of. In the bottom, we have s squared plus 1 squared. So I want 1 on top. Oh, good. That is what I had on top. Now, each of these are in standard form. It's negative 2 times that. The thing is, we're supposed to just memorize things like that. This is either a sine or a cosine. Since it has s on top, it's going to be the cosine. It's going to be the cosine of, that's 2 squared, so 2t, minus 1/2. Since it doesn't have s on top, I use the one that does have s. It's the sine of 2t, plus 2 times this. Well, k is 1, and since it does have s on top, I go to the c function, the cosine function, or the cosine of 1k, or just k, minus this bottom one. It has k on top, so I start with s, and k is 1, the cosine of 1t, I meant to say. Cosine of 1t, just like the one before, the cosine of 1t or t, cosine of t. And there's the answer. So you have to know some Laplace transformations. Now we're going to talk about taking derivatives, or taking the Laplace transform of derivatives. L of f prime of t, well, this is integral from 0 to infinity of e to the negative st times f prime of t dt. We're going to solve this by parts, by letting u be this function. Well, then dv is everything left over, everything. Well, then v will just be f of t, and du will be negative s e to the negative st. And we know that this equals u times v, u times v from 0 to infinity minus the integral of v du, that product. So that product is negative itself, so it can become plus. I'm going to bring the s out in front, and it's this should have the dt. It's going to be this times that, e to the negative st dt. Okay, so let us do this one. E to the negative st times f of t from 0 to infinity. Well, when you plug infinity in here, you're going to get 0. We're going to assume that f of t is bounded. But e to the negative st, e to the negative st just takes off. Right, e to the st takes off. Remember, this is in the bottom as e to the st. It takes off. Goes up to infinity. Now when you plug in 0, you just get f of 0. So this is equal to this s integral of e to the negative st dt minus f of 0. So let's continue one more line equals s. Okay. Always sloppy mistakes. Let's do the parts again. If u is e to the negative st, then du is negative s e to the negative st dt. And dv is f prime of t, so v is f of t. Now, I wrote down u times v, u times v from 0 to infinity, minus the integral from 0 to infinity of v du. This product, well, it has a minus sign. The s I'll put in front, and we have e to the negative st times f of t dt. So or do you multiply these three things and are up to you. I did this times that times that. So where's my sloppy mistake? I forgot to put f of t there. I forgot to put f of t. Okay, so there it is. Now this integral is the Laplace of f of t minus f of 0. So what do we have? We have that this is equal to that. In general, if you have the Laplace of the nth derivative of t, you're gonna have s to the n times the Laplace of f of t. That you're definitely gonna have. Then you start taking away. First let's look at an example. Suppose you have the third derivative. Well, it's going to be s to the 3 times the Laplace of f of t. It's definitely going to be that. Now, everything else is going to be minus. It's going to be minus s squared, and then minus s to the first, and then minus s to the 0. And it's going to have f of 0, f prime of 0, and f double prime of 0. Notice, now, in this first one, it's 0 derivative. Notice that they always add up to 2. S to the first, 1 prime, is 2. 0 plus 2 primes is 2. 0 plus 2 is 2. Okay, of course, you don't have to write down that 1. S is s to the 1. And you don't have to write down s to the 0. Of course, it is 1. So, in the line above, we're going to have s to the n times the linear transform of s to the t. Notice that that and that will match. And then everything else is minus. We have s to the n minus 1. Now notice that when this was 3, these numbers added up to 1 less. 1 plus 1 prime is 2. 0 plus 2 is 2. So now everything else is going to add up to n minus 1. So I'm going to have the 0th derivative. And we're always evaluating at 0. Then 1 less, n minus 2. So I have to have 1 prime. All the way down to eventually s to the 0 times the n minus first derivative evaluated at 0. Okay, know that formula. This is just going to come up all the time. So now let's work out a quick problem. We're going to solve a differential equation now using Laplace transforms and inverse Laplace transforms. It's going to be very cool. We have dy dt plus 2y is equal to 11 sinus 3t. And y is 0 is 5. So I'm going to take the Laplace of both sides. I'm going to take the Laplace of the left side and the Laplace of the right side. Remember, Laplace is linear. So I can take the Laplace of the first term plus the Laplace of the second term. Plus the Laplace of 2y. And this is going to equal to the Laplace of the right-hand side. Now, the Laplace of y prime, this is s times the Laplace of y minus y or f of 0. Plus 2 times, I can factor out that 2. 2 times the Laplace of y. And this is equal to, on the right side, remember the 11 can come out, and the Laplace of the sine of 3t, well, you're going to have s squared plus, that's k squared. Now, do you put s on the top? No, because that starts with s. So you put k on the top. And y is 0 is just 5. So now we have a number of L of y's. We have s of these, and I'm adding 2 of them. So we have s plus 2's L of y. Let's not forget to take away the 5. And let's not forget on the right side that we know what k is. K is 2. Sorry, k is 3. So when I square it, I get 9. 11 times 3 is 33. So this is what I have. I'll add the 5. So now L of y is just going to be the right-hand side divided by this number, s plus 2. So in the numerator, let's get a common denominator. Yes, 33 over s squared plus 9. And for the 5, I'm going to multiply top and bottom by s squared plus 9. So actually, it's 33 plus 5 times s squared plus 9. And at this point, I hope you know that the s plus 2 just comes up here as well. So L of y is 33 plus 45. 33 and 45 is 78 plus 5s squared. 5s squared plus 78 all over s squared plus 9 times s plus 2. Now, I'm beginning to wonder if we really wanted to get a common denominator. I'm going to say no. I'm sorry. I'm going to say no. We could. We'll probably just make the problem harder. So we have plus 5 over s plus 2. So we have this first fraction is 33 over s squared plus 9 times the s plus 2 plus 5 over s plus 2. So let me erase most of this. So that tells me that y, which is a function of t, y of t, I'm just going to interchange those two, is equal to L of 33 over s squared plus 9 times s plus 2 plus 5 over s plus 2. Except if you switch these two, the L has to become L inverse. Now, I know L inverse of that. And that's going to be an easy one. L inverse of 5 over s plus 2. You can factor out the 5. And you have 1 over s plus 2. Now 2, you don't worry about. Just remember that this bottom is the same as s minus negative 2. So we have the 5 in front, and the inverse Laplace transformation of that will be e to the negative 2. So it's 5e to the negative 2t. So that's an easy one. The first one is going to be the one that's a little bit difficult. Alright, so we just do the following. We want to write 33 over s squared plus 9 times s plus 2 as something over s squared plus 9 plus something over s plus 2. S squared plus 9 is a second degree equation. So I put a first degree on top. Ax plus b. And since the second fraction is linear in the bottom, I just put a constant on top. And then I want to write these two fractions with the same denominator. Namely, s squared plus 9 times s plus 2. The first fraction is a plus b over s squared plus 9. Out of nowhere, I have s plus 2 in the bottom. I have to multiply the top by s plus 2. Plus c over s plus 2. But I have c over s squared plus 9 times s plus 2. Out of nowhere, s squared plus 9. So I put that. Now, with respect to these two fractions, they both have the same denominator. That just tells me that the numerators are equal. That is, 33 is equal to ax plus b, I'm going to make one change, times s plus 2 plus c times s squared plus 9. In this problem, the variable was not x, but rather the letter s. Okay. So I have that 33 is as squared plus 2as plus bs plus 2b plus cs squared plus 9c. So the right hand side, I have some s squares. I have a plus c s squares. And I also have a number of s's. I have 2a plus b s's plus I have a constant 2b plus 9c. The reason I cross out stuff is just in case in the end maybe 2b was not crossed off. So I say, oh, I forgot to write the constant 2b, but I did write it. And this is equal to 33. Just be mathematically mature enough to know that 33 is 0s squares, which is 0, plus 0s's, which is another 0. 0 plus 0, of course, is 0. And then you add 33. So the number of s squares is 0. The number of s's is 0. And the constant is 33. So I have 3 equations and 2 unknowns. The first equation tells me that a plus c is 0, right here. Well, that tells me that a is negative c. So I'm going to eliminate a's by just putting negative c. So the second equation tells me 2a's, which is negative 2c, plus b is 0. Well, you know what? Bringing that to the other side, that tells me that b is 2c's. So instead of a, I can write c's. Instead of b's, I can write c's. And instead of c's, I can write c. So 2b plus 9c. On one hand, it equals 33. On the other hand, b is 2c. So that's 2c. Times 2 is 4c's. Plus 9c's is 13c's. And that equals 33. Dividing by 13, divide that side by 13, get c. Divide that by 13, you get 33 over 13. So now we have what c equals. Well, I know a is just c with a negative sign in front. So a is negative 33 over 13. And b is twice c. You double c, you get 66 over 13. So now I have a, b's, and c's. Okay, so let's go back and plug in the values. Again, I still have that typo. X should be the letter S. We have AS plus B. But A is negative 33 over 13. So we have 33 over S squared plus 9 times S plus 2. That's this piece. And it equals to that piece. Where A is negative 33 over 13. S over S squared plus 9 plus B. B is 66 over 13 plus C, 33 over 13 over S plus 2. Okay, so we can get rid of almost all of this. And then I can say that the top line is equal to Laplace inverse of 33 of this, that is of this, which equals that. Negative 33 over 13s plus 66 over 13 all over s squared plus 9 plus 33 over 13 over s plus 2 plus 5 over s plus 2. Now, these two terms I'll try to add. 5 is equal to something over 13. Well, 13 times 5, you should know, is 65. So we have 33 over 13 over s plus 2. And you're going to add 65 over 13 over s plus 2. Since the denominators are the same, you add the numerators. So it's this plus that. Oh, those denominators are the same. They add the numerators and it looks like you get 98. So I'm going to erase this one and I'm going to write 98 over 13. Okay. We still have a lot of simplification that we're going to do. This becomes the inverse of this over s squared plus 9. Again, you can skip any of these steps that you see. Plus 66 over 13 over s squared plus 9. Plus 98 over 13 over s plus 2. So it's the Laplace inverse of this, plus the inverse Laplace of that, plus the inverse Laplace of that. Now, when you take the inverse Laplace of the first, you can factor out that 33 over 13. And just take the inverse of s over s squared plus 9. Plus, when you take the Laplace of the second fraction, you can factor out the constant. And just take the inverse of 1 over s squared plus 9 plus the inverse Laplace of the third. You can factor out the constant and just take the Laplace inverse of 1 over s plus 2. Okay. Now, this first Laplace is done. Just remember that 9 is 3 squared. Since there's s on the top, s is in sign, we write cosine of kt. K is 3. K is what's being squared here, namely 3. 3t plus 16 over 13 times this. Now we don't have s on the top, so we have to have k. Well, the 9 is k squared. That is, k is 3. So I put a 3 on the top, but then I have to put a 3 on the bottom. And I'll definitely say 3 goes into 66 22 times. And now, the Laplace inverse of this, since we have k on the top, we don't have s on the top, so I start with s. S, or sine of k times t, plus 19 over 18 e to the, I'm really taking Laplace inverse of s of 1 over s minus a negative 2. Well, that's e to that number t. And there is your answer. You have to get good at partial fractions. To do the next problem, I'm going to prove a little lemma. A lemma is a baby theorem. Lemma. The Laplace of 0, the Laplace of 0 is equal to 0. Proof. The standard way of proving it. We know that 0 is equal to 0 plus 0. So the Laplace of the left side is equal to the Laplace of the right side. But the right side, I don't care what these things are. If you have the Laplace of a sum, you can take the sum of the Laplace. L of 0 plus L of 0. Now whatever L of 0 is, whatever it is, you have two of them. Well, if this is equal to 2 times itself, then it must equal 0. You can do it in more baby steps. We have this equation on the bottom. If I take away L of 0 from both sides, the right side just gives me 1 L of 0. The left side is 0. So I did prove what I wanted. So now, suppose you have 3 times dy dt plus y is equal to 0. And y of 0 is 4. So we take L of both sides. To save space, let's do that right here. So distributing and factoring out constants, L of 3 times dy dt is 3 times L of dy dt plus L of y. And the right hand side is 0. We just proved that L of 0 is 0. Now, L of dy dt, that's L of y minus y of 0. That's that theorem that I didn't prove. This theorem right here. I only proved it when n was 1. When n was 1. Actually, it's s times L of y plus y of 0. And okay, plus L of y is 0. Now remember, this is 4. So distributing, we have 3s L of y's minus 12. 3 times 4 is 12, plus 1 more L of y. And that equals 0. So I add the L of y's. How many L of y's I have? The answer is not 2. Here I have 3 s's of them, and here I'm adding 1 more. So I have 3s plus 1 L of y's. Minus 12 is 0. Well, then this must be 12. And when you take away 12, there's only one number that you can take 12 away from and get 0. And that number is 12. So 3s plus 1's L of y's must equal 12. Dividing by this number, we learn that L of y is 12 over 3s plus 1. Now, I never took L of anything and had 3 s's in the bottom. There's always 1 s. So you know what? I'm going to divide every term by 3. 12 over 3, 3s over 3 is s, plus 1/3. Now we're in really good position because L of y is equal to that. I'm going to switch the y and 4 over s plus 1/3. So we know that y of t, is equal to Laplace inverse of 4 over s plus 1/3. Now, remember, we know the Laplace inverse of 1 over s minus a. It's e to the at. Okay, we know that. So I want a 1 on the top. So I factor out the 4. So y of t is 4. The Laplace inverse of 1 over s plus 1/3. But you need to be mathematically mature enough to know that when you don't want an addition, you can always convert it to subtraction. Instead of adding 1/3, we can take away a negative 1/3. So it's 4e to that number t. Negative 1/3 times t. You can either leave it like that, or you can say e to the negative t over 3. So that's what y of t equals, or that is what y of t equals. Pretty nice. We solved a differential equation with an initial value by using Laplace transformations and actually as well as inverse transforms. Try a couple of more. dy dt minus y is 1 and y is 0 is 0. So I take the Laplace transformation of the left side and I take the Laplace transformation of the right hand side. So on the left side we get the Laplace of dy dt minus the Laplace of y. And for now I'll just keep the right side like that. Now the Laplace of dy dt, and that's where that theorem comes from, it's the Laplace of s times the Laplace of y minus y of 0. What I've written down so far was just this, minus the Laplace of y, and it equals to this, which is one of those 7 we should know, is 1 over s. Now, y is 0 was given to be 0. So basically we have s minus 1 Laplace of y's, and that's 1 over s. Okay. So dividing both sides by that quantity, the left side just becomes L of y, and the right side becomes 1 over s times s minus 1. And you should see it by now. We want to write this as something over s plus something over s minus 1. Since they're both linear in the bottom, I just put constants on the top. The a gets multiplied by s minus 1, and the d gets multiplied by s. That way, that's the denominator. After all, if you did this division, the s minus 1s would cancel, and you would just get 1a over s. And if you did this division, the s's would cancel, and you would just get b over s minus 1. So L of y is, now this numerator, well, let's just worry about the numerator. 1 over s times s minus 1, this is equal to this fraction, which also has the same denominator. It has AS's plus BS's. It has A plus BS's minus A. The left side, it has no S's plus A. So negative A is the constant. So a is negative 1. Okay, wonderful. And a plus b is 0. So b is 1. So a is negative 1 and b is positive 1. So L of y is negative 1 over s plus 1 over s minus 1. But that's somewhat simple to solve. Just going to recopy it. L of y is negative 1 over s plus 1 over s minus 1. So y, if I interchange this and that, y is equal to L of negative 1 over s plus 1 over s minus 1. Except when you switch, you have to put inverse. So this becomes the inverse of negative 1 over s plus the Laplace inverse of 1 over s minus 1. In the first fraction, I'm going to factor out the negative 1, or just the negative sign if you prefer, and I get 1 over s. Remember, s is the same as s minus 0, plus L inverse of 1 over s minus 1. So this is negative, and this is just e to the 0t. E to the 0t. But 0t is 0, and e to the 0 is 1. Plus, this one is e to the 1t, or just t. And there is your answer. Okay, let's try one more. Let it be a higher power for the derivative, and we'll go from there. Y triple prime plus 2y double prime plus 3y prime plus 6y. Let's suppose it equals to e to the negative t. And the initial values are y is 0 is 0, y prime is 0 is 0, and y double prime of 0 is 1. So we take the Laplace of both sides. The Laplace of the left side equals to the Laplace of the right side. Now, the Laplace of the left side is the Laplace of y triple prime, which is s cubed, the Laplace of y, minus s squared, s of 0, minus s, f prime of 0, minus f double prime of 0. That's just L of y prime, y triple prime. Plus, as it says plus, L of 2y double prime. Well, the 2 I can factor out. That is, this is just 2 times the Laplace of y double prime. But the Laplace of y double prime is this. It's s squared L of y minus s, s of 0, minus f prime of 0. Okay, plus the Laplace of 3y prime. Well, the 3 can factor out times the Laplace of y prime. But the Laplace of y prime is nothing more than s, the Laplace of y, minus f of 0. That's the Laplace of y prime. Plus the Laplace of 6y, or 6 times the Laplace of y. And this is equal to the Laplace of this. Well, that's a minus 1 there. So it's 1 over s minus negative 1, or 1 over s plus 1. Now, most of the, y of 0 is 0, and y prime of 0 is 0. Or f of 0 is 0, and f prime of 0 is 0. So this is 0, which means this whole term is 0. And f prime is 0 is 0, so that whole term is 0. This is 0, which means the whole term is 0, and that's 0. And f double prime of 0 is 1. So let's not forget to take away 1 at the end. So, well, actually, let me write down the f of 1, and that's also 0. So what we have is a number of L of y's. We have a number of L of y's. How many do we have? Well, right here we have s cubed. This is gone. This is gone. I already wrote down minus 1. And here we have 2s squared L of y's. So plus 2s squared. And this is gone and this is gone. And now we have plus 3s L of y's. This is gone. Plus 6 L of y's. And this is equal to 1 over s plus 1. So I'm going to add 1 to both sides. The left side is now this. When I add 1, I'll write the 1 this way. For obvious reasons. Because in addition, I want the bottoms to be the same. S plus 1. And the top is going to be s plus 2. So if we have s plus 1. If here's the number line and here's s, then you add 1. Well, that's s plus 1. But then you add another 1. So now you're at s plus 2. Dividing by how many L of y's we have, that is dividing by this number, we get L of y is this, s plus 2 over s plus 1 divided by this number, s cubed plus 2s squared plus 3s plus 6. The whole problem comes down to solving this inverse. I know that if I interchange what's in that bracket with what's in that bracket, we get that y of t is not equal to L of s plus 2 over s plus 1 times s cubed plus 2s squared plus 3s plus 6. It's not that, but rather it's the inverse of that. So let's try to factor this bottom. S plus 1 already factored. Let's look at that one. We have s cubed plus 2s squared plus 3s plus 6. I would try to factor this by grouping. Since that's the plus, I don't have to change that bottom. In the first bracket, can factor out an s squared. S squared times s gives us s cubed. Plus s squared times 2 gives me 2s squared. The second bracket can factor out a 3. 3 times s gives me 3s, plus 3 times 2 gives me 6. And you know you're doing this right if what's left over are the same. We're adding s plus 2's. And how many s plus 2's do we have? We only have s squared plus 3 of them. So that second factor in the bottom is just s squared plus 3 times s plus 2. So I can come here, erase it, and put what it equals. It equals s squared plus 3 times s plus 2. Then you say, oh, the s plus 2's cancel the 1. So let's write down very carefully what survived. 1 on top, s plus 1, s squared plus 3 on the bottom. So that is, the inverse Laplace of that. Now, I don't know any inverse Laplace functions that look like what's in that bracket. I have to change the way it looks. And based on what we've done so many times already, we want to write this as partial, as something over s plus 1 plus something over s squared plus 3. We use the partial fraction technique to do that. Since this fraction is linear, I put a constant on top since that denominator. Since the second denominator is quadratic, second degree, I put a linear function on top. And again, the variable is s. Now, to get these denominators to be the same, in the first fraction, I have to multiply by s squared plus 3 top and bottom. And in the second fraction, by s plus 1 top and bottom. When you add these two fractions, the bottoms are going to be the same. In fact, it's the same as this. So the numerators are going to have to be the same. On the left side is 1, and the right side is as squared plus 3a plus bs squared plus bs plus cs plus c. So the right-hand side is going to be a number of s squares plus a number of s's plus a constant. The s squared, well, we have a of them, and I'm adding b more. So we have a plus b s squared. And for s's, we have b plus c of them. And for constants, we have 3a plus c. And this 1 is the same as 0s squared plus 0s plus 1. That is, this is 0, this is 0, and this is 1. So a plus b must be 0. B plus c must be 0. And 3a plus c must be 1. Well, this tells me that b is negative a. Okay? So b, which I write this way, b plus c is 0. That means c must equal a. Bring that to the other side. So c is a. Bring this, the negative a to the other side is positive a. Alright, so c is a. So this is 3c plus another c, which is 4c, which equals to a. 1, excuse me. It equals 1. So c is 1/4. But c is the same as a. That is, a is the same as c. A is 1/4. And b is negative of whatever a is. So there it is. Make sure this works. Okay. Those are the three values. Let me put them down here, please. A is 1/4. B is negative 1/4. And C is 1/4. So let's rewrite this, that is this, plugging in the correct values for the A and the B. And we don't need the multiplication of 1 anymore. So we have that 1 over s plus 1 times s squared plus 3 is equal to a over s plus 1, a quarter over s plus 1, plus b. I'm going to first say bs over s squared plus 3, and then plus c over s squared plus 3. So since b is a negative, it's minus 1 quarter s over s squared plus 3 plus c, which is 1 quarter over s squared plus 3. And we know that y of t is the Laplace inverse of this. So y of t is the Laplace inverse of this. The Laplace inverse of that. That is, it's the Laplace inverse of that fraction, where I can bring the quarter in front, minus the Laplace of this, where I can bring the quarter in front. Plus the Laplace of that, Laplace inverse of that, where I can bring the quarter in front. Okay. Now most of these, if not all of them, are really straightforward. The reason I said most of them is some of them might need a constant or something. Well, remember, this bottom in the first fraction is the same as s minus a negative 1. So whenever you have 1 over s minus a, it's the quarter in front, times e to the a, negative 1, t, minus, what is that minus? Now, keep in mind that that 3 is the square root of 3 squared. So k is square root of 3. And when you have s on top and s squared plus k squared in the bottom, and it's a Laplace inverse, well, since this starts with s, we're going to go c. 1 quarter the cosine of kt. Plus, now, this here is the square root of 3 squared. Well, I don't have s on the top, so I better have k on the top. I better put square root of 3 on the top. That means I have to put square root of 3 in the bottom. But square root of 3 in the bottom, I don't like that. I'm going to multiply by 1. And I get square root of 3 over 3. That is, I can multiply by square root of 3 over 3. And if you don't believe that, the square root of 3 times square root of 3 is 3, divided by the 3 in the bottom. I really multiplied by 1. Okay, so 1 times square root of 3 is that number, and 3 times 4, or 4 times 3, is, of course, 12. Now, that Laplace inverse is straightforward. Since it doesn't have s on the top, doesn't have s in the numerator, I do write s. It's the sine of kt. K is square root of 3t. And there's the answer. This actually completes the section on inverse transforms and transforms of derivatives. So now we have yet another way of solving differential equations using Laplace transformations and inverse transformations. But you must go over your partial fractions. That's algebra. That shouldn't be bothering you. Okay, good luck.